Okay, guys, we're going to do lessons 16 and 17 today. First part's going to be on complex fractions. Make sure you're reading over this part. But essentially, the two main keys to doing this, we're going to be using the idea that you will, in fact, need a common denominator when adding. And when multiplying, you can multiply by the reciprocal. Now, the idea, the way I would explain what we're going to do with this problem is... recall, like if you had 6 divided by 2/3, for example. Okay, this is your division, and to do division by a fraction, you would multiply by the reciprocal, and that would get rid of that. That's kind of the idea, or the way I would normally do this. They're going to be talking through multiplying top and bottom by the same amount, but the idea is right here on the bottom, I can multiply by the reciprocal, and then so it'd be MD on top, and that's my new bottom, and there's that answer. So you can kind of do this in one step rather than the two steps that they have. So the next problem, they have, a fraction in a fraction, which is in a fraction. So your idea is, if there's a plus sign, you'll need a common denominator, multiply it by the reciprocal to make this into one fraction, and then you'll get a common denominator again. So here's the idea. Fraction within fraction, first thing I did was common denominator. Now that I have just one fraction and another, now I can do the reciprocal, so D moves up top with the MD. Where are we? Right there. MD. And then the BD plus C is my new denominator. Same thing again here. I still have another fraction to get rid of, so I'll need a common denominator. So that denominator is going to be BD plus C, which is why that's there, so we can get this common denominator. Once I have one big fraction, then I can just multiply by the reciprocal. So this moves up top, and this is my new denominator, and that is where this answer comes from. Okay, let's try one over here. Off to the side, here's my problem. So go ahead and write that down. Again, I see subtraction on top and bottom, so before I can do anything else, common denominator on the top and bottom. So my common denominator up here is going to be x squared y squared. So this is missing a y, so this is now going to be a to the third y minus. And this one has y squared, but only one x, so it's missing an x. So up top here, we're going to have 6m squared x. Okay? And then my common denominator again was x squared y squared. On the bottom, okay, we're going to be on the denominator here, same exact denominator. Y squared here, x squared there. We need a common. It's going to be x squared y squared. So this is missing the x squared minus 6t, and this fraction is missing the y squared from the denominator, and again my common denominator is this. Okay, so my first step is done. Now again, when I have a fraction bar, the way I do division by a fraction is I'm going to multiply by the reciprocal. So I'm going to take this denominator, move it up top, and multiply by the reciprocal on the bottom, L squared x squared minus 6ty squared. So that's now gone because I moved it up here and did the reciprocal. And now in a multiplication question, I have the exact same thing on top and bottom, so the x squareds and y squareds cancel. And so I have my top, a to the third y minus 6m squared x over, and then on the bottom I just have that now, L squared x squared minus 6ty squared. Okay, and that's going to be my final answer because it's down to one fraction. Remember, I can't randomly try to cancel anything out. Remember, like these sixes, for example. Think in terms of a problem like this, 5 minus 4 divided by 4. That answer should be 1/4. So in other words, you're not allowed to do that. Say the answer is 5. Okay, so remember the rules for fractions with subtraction. Example 3 in our book changes gears. We're going to abstract equations, which just means you have an equation, your job is to solve for a variable. So undoing some operations. So here's one. that I made up here, solve for d. So I need to get d by itself, so I don't have a whole lot to choose from here. So anytime I have division, I can always multiply to get rid of that. Make sure you do it on both sides. So I'm going to take my 2d minus w, and I'm going to multiply it by this r over here. And on this side of the equation, I was trying to get rid of the denominator, which I did. Okay, now that I'm getting rid of fractions, this problem looks a lot easier. I still have to get the d's by themselves. So I am going to have to distribute this r in order to get that to work. So 2dr minus rw equals d plus 1. Now I'm going to bring this d to this side. So 2dr, I'm going to subtract d. I also need to get anything that doesn't have a d to the other side, so I'm going to add this rw, so now it's positive on this side to go with the plus 1. Now I want to get d by itself, so I'm going to have to factor it out. If I take the d out of there, there's still a 2r, and if I take the d from there, there's nothing left, so I hold that place value with a 1. And finally, division will help me get d by itself. Divide by 2r minus 1. And so my answer for d is what I have right there. rw plus 1 on top and 2r minus 1 on bottom. And I've gotten d by itself. Example number 4 is going to talk about long division. You've done this before, but we're going to look at some maybe more difficult examples, or just make sure you read through that. Again, long division, you're subtracting, so I'm going to kind of concentrate on that. So here's my made-up example. I'm going to divide this number by this one, which means this number is going to go underneath. And this number here is the one on the outside. Now remember, in long division, you take the highest exponent here, and you try and figure out, okay, how does that turn into that? What can I multiply this by to get that? Well, if this has x squared, I would need another x squared to make x to the 4th. Then make sure you distribute that or multiply it to get this next line. So x squared times x squared is x to the 4th, and then plus 2 times x squared is 2x squared. Now remember, in long division, after you multiply, the next step is to subtract this from your initial amount. You may want to put parentheses to remind yourself you're subtracting the entire thing. X to the 4th minus x to the 4th, that's gone, that's the whole idea. But x squared minus 2x squared would actually give me negative 1x squared. You're going to have to be careful with that. Bring down what you haven't used yet. And again, now you take your first part, how does this become that? Well, it already has x squared, it doesn't have the negative sign, so I'm going to need a negative 1. Negative 1 times x squared, right there, and negative 1 times positive 2 is negative 2. Notice I left some space there because I'm subtracting like terms only. This will be part of my answer. Make sure you're subtracting this entire thing, so maybe put parentheses. These cancel. I have my negative x to bring down, and then my like terms here, 1 minus negative actually works like a plus then. 1 plus 2 is positive 3. And so this is my remainder. So if you remember, your answer is x squared minus 1, that was what's up top, and then plus whatever your remainder is, in this case, negative x plus 3 over, and then you put it over what you divided by, x squared plus 2. So this is my answer. Now most of the time, if this was multiple choice, you would not see this as an answer. Instead, you would see this negative come out front as a minus sign, and then make sure you distribute that through. So the x becomes positive, which is ultimately what you want, but then the 3 would not be anymore because it was factored out front. And there's my answer. Now the directions say to check that answer. What you should do is take that and multiply it by what you divided by and make sure you got the original amount. What I would suggest is taking this and distributing it into this, not the other way around, because if I go this way, the x squared plus 2's, you can just cancel those out when you multiply it, and then you'll get that answer. So there's the first part of your assignment right there, 1 to 30. Of course, you can ask me if you have any questions. We are going to do lesson 17 real fast. Just one quick proof of similarity. The key here, to prove two triangles are similar, you either need two angles that are the same. You only need two, not three, because they had to 180, so if two angles are the same, the third one has to be. Or you can deal with their sides, but remember, similarity means they look the same, but one is bigger or smaller. So the proportional sides will work also. Most of the time you're dealing with angles, like in this example or the ones in your book. Okay, by the way, the Pythagorean theorem ones, we actually already did that, did the second one in class, and this first one's worth looking at as well, but I'd skipped ahead here on the video for the second part. So you're looking at proofs like this. Now remember when we talked in class, you're looking for stuff that we've talked about before, like in this one, vertical angles are the same. So you look in your proof, sure enough, vertical angles. As long as you have two angles in each triangle the same, then the triangles have to be similar. This step is kind of a waste for me. AA is enough to show triangles are the same. Same thing here. If you see parallel lines, you should automatically look for alternate interior or corresponding or alternate exterior, which is what they used here. And then here, this is the example with some side lengths. They have to give you side lengths for you to show that they are proportional, or they have the same 3:2 ratio between the sides. So that would be an example of side angle side. So here's an example that I found. All right, let's see, we were given that these two lines are parallel. So I go over to my picture. If these are parallel, there's usually going to be a little arrow saying that they are parallel. Okay, if they're parallel, we should be trained to look for certain types of angles. And in this case, this angle right here is in a corresponding location with that angle right there. They have to be the same. If these lines are parallel cut by a transversal, the corresponding angles have to be the same. If you don't see it, maybe extend the lines. Maybe it'll look a little bit easier. You know, two lines, one transversal, corresponding angles have to be the same. Okay, you can either use a second set of corresponding angles. All right, that's not the notation we use. One with that, boom, boom. So now you have your two angles, which is all you need, or you can do overkill, which says that angle A is part of both triangles, this little one and this big one that we're trying to prove are similar. So my proof would look like this. Okay, we just marked in my picture that this angle and this angle are the same. So ADE and ACB are the same. So angle ADE is congruent to, as in the same size, angle ACE in that picture. The reason we know that is because if the lines are parallel, again, I usually use some sort of notation. If the lines are parallel, or a shorter word for this example, if the lines are parallel, then corresponding, that's the word I basically would be looking for if you were doing your own proof. Definitely need that vocab term. The corresponding angles are going to be congruent. And then we said there was another set, so I don't even have to write a new any more work, or step 3, I mean, because I know that in that picture AEB was similar to angle, okay, that one was the same as that one, angle B, ABC, for the same reason. So I'm just going to join it with that one. I don't have to rewrite that reason. That right there is enough to say that these two triangles in this picture, AED, I put AEB, this should have been D. Okay, AED is similar to, meaning they're not the same size, but they do have the same angles, triangle ABC. And the reason we know that, and we would just put AA for angle, angle. Okay, so these are the problems I would like you to do from section number 17. 4 to 13, 21, 26, 27. Thank you, and we'll see you Tuesday.